Hi guys, and welcome to the video on normal curves and z-scores. Alright guys, so in this video, this is going to be a tough one, but we're going to get through it. We're going to learn how to use a normal curve to fit a set of data and plot deviations to talk about grouping. Why? Because human traits and characteristics fall on normal curves. Pretty much any characteristic you can think of is on one of these kinds of curves. And you'll know you're successful when you can use a normal curve to plot data and then calculate how many people or things fall within the deviations of that curve. So let's get started. So first and foremost, what is a normal curve? And I'll scroll down in a bit. You've probably seen it before. It's commonly referred to as a bell curve. A normal curve is the probability distribution curve of a normal random variable. So when we say that, okay guys, what those words mean is normal random variable is a single variable, and it is something like that we can measure. Give you an example of a normal random variable. Height would be a normal random variable. Another one, weight, intelligence, test scores are all parts of normal random variables. They're single too. All right, we're not doubling up. We don't need x's and y's. We have one list of data. The bell curve, the normal curve, is a graphical representation of this normal distribution. So if I scroll down, you can kind of get an idea of what's going on here. Most things, and I'm going to talk about it in the next one, fall into the middle, and then between the next two, almost everything falls in, and by the time you get to the very ends, basically everything is fallen within that distance. So right now, what we have down here is the mean, and that's the same mean that you've calculated a million times before. And then we also have that symbol here means deviations. So moving one deviation down, moving a second, a third, and so on. We'll get some practice, and we'll see this on our examples. So let's get to the next slide. What use is a normal curve? Normal curves are used to plot a lot of human attributes. Like I said before, height, intelligence, test scores, weight. These are described with an average, the mean, and then people or data points fall within the standard deviations of the mean. These two measurements are the exact same two we calculated in our previous section 6.1. Okay, we can calculate them with a graphing calculator. These standard deviations correspond to percentiles as well. Thinking about what they mean, the mean represents the 50th percentile. Exactly average. And then each deviation reaches a new percentile. A single deviation up would reach all the way up to the 84th percentile of all people. By the time you get to the second deviation away from the mean, you're talking about being 97.5%, of all people. And then by the time you get to the final third deviation, you're talking about 99.7% of all of the people. And that's the 68, 95, and 99.7 rule. Okay? Most people fall within 68% of one deviation. They fall within 95% of two deviations, or they fall within 99.7% of all people fall within 3 standard deviations of the mean. So let's take a look at some z-scores, or what the word z-scores means. A z-score is called a standard score. Okay, it gives you an idea of how far from the mean a data point is. More precisely, it's really a measure of how many standard deviations below or above the population average that a data point actually is. So to calculate a z-score, the formula is that the z-score, z, is equal to the data point, and then you're going to take away the mean from that data point and divide that amount by the standard deviation of the entire data set. That will give you a z-score, and it will tell you where on the chart to put that piece of data. So, continuing. Fitting data to a normal curve. What you're going to do is to fit your data onto a normal curve, you calculate the mean and the standard deviation of the data, and then you can take the mean and plot it in the center. And then you add the standard deviation each time to the right or subtract it each time to the left. So let's pretend that I have a mean of 75. And then each standard deviation is 5. To fit this onto my curve, I'm going to put 75 in the middle. Then, every time I add a deviation, I'm going to increase the amount by this. So I'm going to increase this one by 5 to 80. And then I'm going to do it again. And this would be 85. And then I would do it one last time to mark the third one of 90. If I had a fourth deviation, I could do it, but usually we don't do 4 deviations on a standard curve. We do 3 deviations each way. So then if I wanted, I would go 1 to the left, and so I added this way and this way and this way. Now when I'm going to the left, I'm going to subtract. So from 75, this would be a 70. And then I'm going to do it again and subtract, and this would be 65. And I'm going to go do it again, and this would be another 5. So this would be 60. So that's pretty much the entire way that you would put your data on a normal curve. All right. Let's do an example problem. The mean weight of 500 college students is 154 pounds, and the standard deviation is 7 pounds. Assuming that the weight is normally distributed, and spoiler alert, guys, weight is an attribute that is normally distributed among people. Plot the data on a normal curve. So they tell me that the mean is 154, and they tell me that each standard deviation is 7. So I know that this middle dash needs to be 154. This needs to be 161. This would be 168. And this last one would be 175. Just so that you guys know exactly where that came from, it's because I'm moving to the right, so I'm going to add the standard deviation. So I'm going to add a standard deviation here, and then I'm going to do it again. I'm going to add again, and then I'm going to add again. So actually, I want to put the plus sign down below. So now the other way, I'm going to take away a standard deviation, okay? I'm going to take away one standard deviation. So this will be 147. This will be 140. And finally, this will be 133. Okay, so there we have all of the possible standard, or we have all of the markers on our normal curve. The next thing that we need to do is we need to start looking at calculating the number of students that weigh such and such. Between 133 and 168. So right here is our 133, and right here is 168. So this is 2 standard deviations, 1 standard deviation, 2 standard deviations this way. So we went plus 2 this way. My 2 looks a little bad. And then it is 1, 2, 3 standard deviations this way. So it's minus 3 standard deviations this way. So what that means is that between 1 standard deviation, 68% of all people would be within that distance. Well, if it's 2 standard deviations, and it is in this case, all right, we have, looking at our basic normal curve, it would be the 34% and then plus the additional percentage from here to here. For the second standard deviation, and then we're going to have to add the additional third this way. So this is a total of 5 standard deviations. So essentially what's going to happen is we need to look at our basic normal curve. So I have to go back a couple pages really quick. All right, it's going to be these boxes here. We need to check this one, this one, this one, this one, and this one. So we need to add up all of those percentages, 2.14 plus 13.59 plus 34.13 plus 34.13 plus 13.59. So when I go back, I calculated that 97.58% of all people, and I spelled people wrong, 97.58% of all people are in this category. So this is the 34.13. I'm going to put this up here just to be a helpful reminder so that I don't have to go back a second time. 34.13. In here was 13.59%. That was a percent. In here, that was again also 13.59%. These percentages, the 13.59, the 34.13, they don't change ever on a normal curve. They're always the same. So that's how I'm taking them from a previous normal curve and using them here. And then I got to go back to look up the last two. I know that this end one is 0.14%. And then beyond 133 would be 0.14%. The last one is 2.14%. So the last one here is 2.14%, which would be down in here and also in here. So 97.58% of all people, which I'm going to then multiply times the 500, and that will tell me the proportion of people. So I'm going to take that and multiply it by 500, because that's how many people are in the grouping, and that is 488 people. So there are 488 people that weigh between 133 and 168. So the next question is, how many people weigh more than 175 pounds? So what I have is right here, I can already see that it's just this standard deviation up. So it's only this amount of people here for B. So we're going to take the 0.14% of all people. That's the only people who meet this category, or meet this criteria, excuse me. And we are going to multiply that by the 500 people again. And that equals around, I did that 0.0. It's 0.7, which we would round up to one person. So there is one person in this entire 500 person data set that weighs above 175 pounds. Continuing, less than 140. So right here, 140 is this deviation right here. So I'm going to use these two combined. So I'm going to use 2.14 plus 0.14 gives me, it's 2.28% of all people. And I'm going to multiply that by 500. And when I do so, that is 11.4, which we're going to go ahead and, so 11.4, which we're going to change to, we're going to round to 11 people. And it appears that I put less than 140 twice. I'm going to change this to be less than 147 was what it was supposed to be, excuse me. Less than 147 pounds. So what I have is I'm going to add the previous two plus this additional third one. So it's going to be 2.28 plus 13.59% of all people. 15.87% of all people fit in this category. So I'm going to multiply that by the 500 people. And when I do, I get 79.4, which I would keep as 79 people. So 79 people of my 500 were below 147. All right. I know that seems confusing, but as long as you remember those numbers, okay, the 0.14, 2.14, 13.59, 34.13, all the way up both ways, this should be no problem. All right. The average score of a statistics test, so when they say average, they're talking about mean. So the mean here is an 85, and I have a standard deviation of 10. Okay, so what that means is if I were to make my normal curve, and it's a haphazard one, so thanks for bearing with me on this one. I'd have my 85 here, and then it would go 95 for one deviation, 105 for the next one, 115 for the last one this way. It would be a 75 here, a 65, and then a 55. So find the probability of a random score falling between a 75 and a 95. So I note that a 75 and a 95 are both one standard deviation away. So it's minus one standard deviation here and plus one standard deviation here. If I look at my normal curve from before, these boxes were 34.13%, both of them, and in here is also 34.13%. So if I go ahead and I combine those amounts, 34.13% plus another 34.13%, I would get 68.26%. So I have, if I pick a score at random, any score out of my statistics class here, because it is one standard deviation to the left and one standard deviation to the right as my endpoints, I have a 68.26% chance of picking a score between a 75 and a 95. Continuing. Suppose that a particular medical procedure has a cost that is approximately normally distributed, okay? With a mean of $19,800, so it's a $19,800 average, and it has a standard deviation of 2,900. If a patient paid $16,275 for the procedure, what percentile does that place them in? So essentially, what we need to do here is we need to calculate the Z-score. So this is the Z-score. This is where Z-scores come into play. If you are given a data point like this and asked about percentile, that is a kicker for Z-scores. So we're going to use the Z-score formula. So we're going to use the Z-score formula. Z is equal to the data point, which is X, take away the mean, divided by the standard deviation. So I'm going to go ahead and push in all the data. I've got the 16,275, take away the average, and that's going to be divided by the standard deviation, 2,900. So the Z-score here, I'm going to do the top first of 16,275, take away the 19,800, is negative 3,525, which when divided by my standard deviation gives me a Z-score of negative 1.22, and you want to round it to 2 decimal places. So I'm going to give you guys a Z-score table on your, if in addition to your packet. What you're going to do is you're going to look up that Z-score, okay? This Z-score can be found in the row of negative 1.2 and then negative 1.22. So that means that the score there, so negative 1, so a z-score of negative 1.22 has a percentage of 11.12%. So if you were to draw the normal curve, and I'm just drawing a really, that is not a good normal curve at all. If I were to draw my normal curve, my 1.22 would be approximately here. So this is where my data point actually is. This is where, so if this is my mean of 19,800, the data point that we just calculated a z-score for is right here, 16,275, which according to this places it in the 11th, not 11%. This would place this in the 11th percentile. So the answer to the question was the percentile of the price was the 11th percentile. All right. And then we move on to the final one. More z-scores. According to a recent study, the average height of a male was 5 foot 9 inches, so 69 inches is the mean. And the standard deviation was 2.7 inches. So both of those are marked with quotation marks for inches because that's shorthand for inches. If a man has a z-score of 1.2, what is his estimated height? So what we're going to do is use the formula. He has a z-score of 1.2, and we don't know his actual height, but we do know the mean is 69 over 2.7. So we can cross multiply. And when we do that, if we were to cross multiply what we have as is, we would do 1.2 times 2.7 and get 3.24 equals x minus 69. So adding 69 to both sides, x is going to equal 72.24. So that's 72, that's about 72 inches tall. Or if you're more of a fan of calculating by height feet, you know, the standard measurement, that would be someone who is 6 feet tall. And then, so what is the range of heights that represents 68% of men? So this is that part of that 68, 95, and 99.7 rule. 68 is all scores within minus or positive 1 standard deviation. Whereas 95 was 2 standard deviations, so this one would be minus 2 or plus 2 standard deviations, and this one is minus 3 or plus 3 standard deviations. So if I take the mean and I subtract a single standard deviation from it, so if I do 69 minus 2.7, so the mean take away single standard deviation, I get 66.3 inches as my lower range, because that is 1 standard deviation. And if I add 2.7 to that, so if I take 69 and add 2.7 to that, I get 71.7 inches. So those are the ranges that represent the height of 68% of all men. So then, what percent of men are taller than 66.3 inches? So if this 66.3 means that I have a z-score. This would be a z-score of -1. So what I would do is look on my z-score table that you guys are going to be given, and -1 has a percentile ranking of, so -1 as a z-score, has a percentile ranking of 15.87. And so what I can do then is say that that is approximately, because this is the percentage of men, or this is the percentile ranking. So I'm going to do 100% of all men, take away the 15.87% that are not that tall, and that will give me a total of, so 100 minus 15.87 gives me a total of 84.13%. So 84.13% of all men are taller than 66.3 inches in this scenario. So that's it, guys. Normal curves, complicated to a degree. They represent all sorts of different data sets. The basic idea of a normal curve is pretty simple. We place the data on the percentile or on the curve and then put in our standard deviations. It gets a little more complicated when we want to go in between those curves and when we start adding things like z-scores in. But just remember that z-scores are a way to calculate where our score lies on the normal curve, and then we're going to use our z-score table to calculate percentiles. Remember, though, that the 68, 95, 99.7 rule is the rule that determines the range of data from the mean, meaning that 65% is one deviation away, 95% of all data is between two deviations, and so on and so forth. We're going to review this more in class, and we're going to practice it in class. I'm going to show you guys directly, but thanks for watching this video, guys, and I'll see you in the next one. See ya.